All right, Jonathan, take it away.
Cool. Yeah, thanks a bunch. I'm super excited to be able to present this work. Work that I did with a collaborator in Russia, Igor Utochkin, as well as Jonas Lau, not Jonas as the agenda says, and my advisors, Tim and Viola. I'm sure
we'll fix that. We'll fix that later. Sorry
I'm sure he's okay. Yeah. So, ensemble statistics, right? Natural scenes are highly complex and contain more sensory information than we could possibly hope to process at any given moment. However, there are a ton of regularities in the visual information that we receive from our environment, which means that compressing this information into some sort of actionable representation may be possible and useful. We can call this type of compressed information ensemble statistics, which can be extracted for all sorts of features in our environment. Now, these statistics can capture the mean or variance of a feature in the environment, which may help us quickly figure out important information about the world we're in. For example, ensemble statistics can allow us to quickly tell what direction people are walking on the sidewalk based upon their average direction of motion, and figure out that we're in a city scene simply from the incredible variance of colors. And in fact, we can simplify this down to a very basic task that we can make subjects do in the lab. For this demo, I'm going to present you a whole bunch of oriented triangles very quickly and ask you to recreate the average orientation with your hand. So I'm going to count it down. 3, 2, 1. So normally I would look out into the crowd and say, wow, everyone's so accurate. This is incredible. But I can't see anyone actually at all right now. So I want you all to judge how well you're able to do that based upon how much your recreated orientation was like this one. So as you can hopefully see, you were all pretty accurate. We can extract this information very quickly from a set of objects. Lots of research has shown that we're sensitive to this average information in the environment. But we don't know how ensemble statistics are computed in the brain and what types of representations we hold in mind during this process. The majority of literature on ensemble perception has suggested that ensembles are computed rapidly and effortlessly, suggesting that only a single ensemble perception is stored in working memory following this very quick process, similar to holding a single item in working memory. However, it could be that we store all of these items in mind and only report a readout of this ensemble information at the time of response, whether it's mean, variance, or even range. Clearly, these two accounts predict that very different amounts of information are stored in working memory following the presentation of the set. So the critical question of the present study is, how much information about items in a set is held in working memory during the process of extracting ensemble statistics? Now, this information isn't available from behavior alone, as the task could successfully be performed either way in theory. Therefore, we used EEG to measure how much information was being held in working memory while subjects performed an ensemble task. In particular, we measured the contralateral delay activity, or CDA. The CDA is a lateralized negativity over posterior scalp that indexes the number of items held in working memory, the amount of information held in working memory. That is, as we can see in this figure from prior research plotting the CDA difference wave, the CDA increases in magnitude as subjects are asked to hold more items or information in working memory. This difference is more negative when subjects are asked to hold 4 items in mind, plotted in green, than when asked to hold 2 items in mind, plotted in blue. So we had an online index of how much information subjects were holding in mind while performing the task. In this study, we had subjects perform a typical ensemble task and adapted the presentation to match visual information across the 2 hemifields of the display, allowing us to measure the CDA. Subjects kept their eyes in the central fixation cross and monitored the locations where the stimuli would appear, indicated by the black placeholder dots here. Then, subjects were given a cue indicating which information they should remember following the presentation, or in the following presentation. This was a 100% valid cue indicating which side would be probed at the end of the trial. This cue was immediately followed by a bilateral presentation of oriented triangles. In this trial, subjects ignored the triangle on the left and remembered the triangle on the right. Then they maintained this information over a 900 millisecond delay, which of course we used to measure the CDA, how much was held in mind. At the end of each trial, subjects were asked to report the orientation of the triangle by continuously recreating the orientation. We had subjects do 3 tasks using this basic format in a block design. I'll remember 1 task, as I just outlined. I'll remember 4 tasks, in which subjects remembered 4 orientations and were randomly probed as to the orientation of one of these 4 triangles. And a report average task, where subjects were told that they would have to recreate the average orientation of the cubed triangles at the end of each trial. These tasks were blocked and performed in a random order, and subjects were explicitly instructed as to what task they would be doing on each block. In order to further reinforce the difference between the remember for and report average task, the probe triangle even appeared in a different location in the report average task, and subjects were never explicitly instructed to remember the items in the report average task, just that they would have to report the average of the items at the end of each trial. Now, from this design, we collected behavioral data indicating how subjects did the task, how well they did on the task, as well as CDA data indicating how much information they were holding in memory. And we'll start by looking at behavioral data, beginning with the error distribution in the remember one task. Here, the x-axis is degrees of error from the probed orientation, and the y-axis is the number of reports. We see that responses were fairly accurate and precise in this task, as you would expect, given that subjects were just remembering one item. But now we'll plot the other two tasks. Here, you'll notice that the remember for condition is a little different. Whereas the remember one and report mean plots have degrees of error from the actual orientation that subjects were trying to recreate, the remember for plot has the x-axis arranged such that errors toward the mean of the set are positive and errors away from the mean of the set are negative. The dotted line in this plot represents what the error distribution would have looked like if subjects were simply reporting the mean, which we've calculated by simulating what would happen in the remember for task if subjects were trying to report the mean with the same precision that they actually reported the mean with, as seen in purple here. The difference between these two distributions is a good indication that subjects were actually trying to remember all four objects and not simply reporting the mean in this task. Now, just to try to summarize what we see in these distributions, I'll start by plotting the average error in each task. On the y-axis, we have error in degrees, and on the x-axis, each task. As we see by the differences in the shifts of these distributions, subjects were most accurate in the remember one task, least accurate in the remember for, and somewhere in between in the report mean. It's worth noting that even though subjects were not simply reporting the mean of the set in the remember for task, they were biased towards the mean of the set. And this replicates previous work demonstrating that even individual memory representations can be influenced by the ensemble characteristics of the set that they're presented within. Additionally, as we can tell from the width of these distributions, the same pattern is present in precision, measured by circular standard deviation. So the behavioral data clearly shows that subjects can do all of these tasks pretty well, and we're not simply reporting the mean in the remember for task. But now, we really want to know how much information was being held in working memory when subjects perform the report average task. Though we can't tell with our behavioral data, we have the CDA to help us figure this out. So I'm going to plot ERP difference waves for each of the tasks, starting with the remember one and remember for tasks. The x-axis here is time from array onset, and the y-axis is microvolts of neural activity with negative up. The gray area of the plot indicates the time period over which we'll be looking at the CDA, and the period highlighted in red indicates when the array was on the screen. The first thing you'll notice is the large difference in CDA magnitude between the remember one and remember for tasks, which is great. That means that we successfully manipulated working memory load. The important question, though, is what the report average task looks like. If ensemble processing occurs quickly and without individual item information, then we would expect that the CDA looks similar to the remember one condition, with the one remembered item being the average orientation. However, if ensemble processing is effortful and involves holding information about the set in working memory, then we would expect that the CDA looks more like the remember for condition, representing the four items over which subjects are averaging. So little drum roll, here we go. In fact, we see that the report average CDA task, it's task CDA, I should say, is nearly identical to what we observe in the remember for task. And just in case you don't believe me, you need cold hard numerical proof, I've plotted the average CDA amplitude across the gray time interval for each condition. You can see that the remember for and report mean conditions are very similar, with the remember one condition being much smaller. I want to pause for a second to point out that this result is actually really surprising, right? Literature on ensemble perception almost entirely states that ensemble perception is an effortless, rapid process that doesn't rely on individual item representations. Now, this suggests, the CDA results, that there needs to be a fairly striking paradigm shift in how we think about ensemble perception. And so to reiterate once more and circle back around to our question from the beginning of the study, information about all items in a set is held in working memory during the process of extracting ensemble statistics. Now this begs the question, why haven't we found evidence of item representations in previous studies? We have a couple ideas, though these aren't the only possible explanations. First of all, the way that individual item memory is typically probed in ensemble tasks is by asking subjects to recreate the feature value of a set member at a particular location, or, as you can see here, do a 2AFC task in choosing which item was present in the set. One possible explanation is that the previous memory tests have been insensitive to whether individual items are actually present. A good deal of the early literature on this topic used stimulus spaces that weren't necessarily uniform, meaning that tests of whether an individual item was at a particular location or in a set could have been particularly difficult, or impossible even, with all the information concurrently present. For example, it personally takes me several saccades across the faces in the 2AFC test here to tell that these are even not the same face. However, it's also possible that we maintain information about all of the items in a set, but let go of the location information about the individual items, because it's not necessary for extracting ensemble statistics. We think of this as a population coding account of ensemble perception, where information about all items is present in the population of neurons coding this information. And we use this population level information to extract ensemble statistics. This account is particularly helpful in that it can explain how we're able to extract the mean, variance, and even range of a set without implicating several different neural mechanisms for rapidly extracting this information. We can extract this information because it's all still there when we're asked. We're maintaining. And that's it. Thanks a bunch to the Brady and Störmer labs, and of course, Igor, who I couldn't fit into this photo, even with the power of Photoshop. Thanks a bunch.
All right, that was a really excellent talk. Please join me in silently congratulating Jonathan. Okay, all right, we already have some questions coming in. Once again, I do encourage trainees to submit their questions. All right, oh man, it's all jumping everywhere. All right, I'm gonna start with Raimundo's question. Very cool results and clear talk. I wonder if the same result would hold for a bigger set size.
Yeah, that's a really great question. And that was the study we were about to start before COVID hit, unfortunately. Yeah, so I think it's interesting in that, right, seeing what the CDA looks like when we push beyond just the 4 items where you might think subjects could be able to hold all of that in memory and go to 6 items, even though I don't think really subjects are holding all of those items necessarily in memory the way we think.
All right, that's great. So I'll do Josh Foster next. All right, great talk. I'm wondering if you think your results would be different if people had to report the mean of all items on the screen. Perhaps it's much faster to extract ensemble statistics when you don't need to select a subset of items.
No, it's a great question. So I think in particular of Chong and Treisman studies from kind of the initial few studies that came out about the idea of ensemble perception that had similar setups to this, right? Where subjects had to report, say, whether it was the same or a different average orientation on the right and left side of fixation. But I agree that, right, there is some sort of kind of effortful part of having to only focus on the right or left side, though we give subjects lots of time to be able to do that. And I think once again, in the future study that we were planning, we have a completely bilateral display, right, where there's no need to filter the right or left side of the screen. So hopefully we will have that answer soon.
Okay, great. We'll have time for one more really fast question. I'm just going to use Benjamin. Timer's now. What happens with larger sets? Oh, we already got that one, didn't we, basically? Yeah.
Redundant question.
Yeah,
but it's a good question. It's a good question.
Go for it, Benjamin.
Yeah. This is just clarification. What was the order of the tasks? Because did you incentivize people to try to remember all 4 by knowing that sometimes they're going to have to report on individual items, and would you get the same result if you just never asked them about individual items?
No, that's a really good question, right? So each subject had a completely random order, and it was counterbalanced across all subjects, the order that is. But of course, right, you could think that maybe subjects are holding all of those items in mind just because they can. I think the strongest argument against that is that, well, if there is some automatic and effortless process for extracting this information, I don't see why subjects would do that. And then secondary, and perhaps more compelling to me, is the fact that subjects hate remembering all 4 of those items. That when subjects come out of that task, the glares that I got opening the EEG chamber were incredible. I really don't believe they would unless that was the way they were doing it.